In this presentation, we're going to continue learning about thermodynamics, and we're going to add entropy into the discussion. Entropy is needed to discuss whether or not a process happens or not. If a process happens spontaneously, then that process can be used to do work, or in other words, to do something else. But if a process is not spontaneous, then you have to put energy in it to get it to happen. So these ideas come into play in a lot of systems where you need to know whether something happens by itself or not. In this entire presentation, my note down here, we are not considering pressure volume work. And that's a simplification. When you go on and take another thermodynamics class, you will deal with taking care of that work too. But basically what we did is we said the change in enthalpy of the reactants, the substances, told us how much heat was given off or absorbed, and we ignored the factor of work being there. So let's look at what I mean by a spontaneous process. And I use this simple example of a ball on a hill, that if a process is spontaneous, and it could be a chemical reaction, but it could be other things as well. A spontaneous reaction is something that just happens, and when it happens, it gives off energy. A non-spontaneous reaction requires you to put work in, so you have to use energy in order for it to occur. And so this is really helpful because it would be nice to know which things can be used to give off energy, to make energy. So that's our question. One of our central questions is to be able to look at a process, a chemical reaction in our case, and decide if it's spontaneous or if it's going to require energy to make it to work. I should also say that there is a difference between a reaction being spontaneous and a reaction happening quickly. How fast it happens is something called kinetics, and other factors come into play with that. Spontaneous is just saying, is it favorable? Is it going to happen? It may be very slow. Okay, so let's kind of back up in what we might have thought. The compounds that have a lower heat of formation are more stable. So we might expect for those, when they go to a more stable state, you might expect that to be favorable because we always use the ball on the hill. So we would expect exothermic reactions to be spontaneous, but there are some endothermic reactions that are spontaneous, and so this is decreasing the heat of reaction, or the enthalpy of the substances is favorable, as in this one, it gives off energy. But there is another factor that allows some endothermic reactions to be spontaneous. The other factor is entropy. Entropy, we use an S for entropy. A lot of times we will talk about it in terms of disorder, and that's kind of an analogy that's given, like a really messy desk versus a really neat desk, and things tend to go to being really messy. It's not really that. It has to do with the energy being spread out and having multiple energy possibilities. But it is kind of easier to think about things being spread out and having lots of disorder to them. So with entropy, you may have known that more entropy or more disorder is favored. So increasing entropy is favored. Entropy is not conserved. It's always increasing for spontaneous processes. An example is diffusion. If allowed to do so, these particles will spread out, and this definitely, when they're spread out, they have more randomness to them. That has more energy, possible energy states. This is definitely an increase in entropy. Let's look at what you might think about some different substances and situations which you think has more entropy. And so for these, it is good to think about the more spread out, the more they're moving, the more random motion, the more entropy it's going to have. So definitely when you compare a solid and a gas, there's more order in the solid, more possible energy states in the gas. When you're comparing temperatures of anything, the warmer it is, the more entropy it has, because when the particles are moving faster, there's more randomness, more possible energy states. And this one is the one that may be different because you tend to think that it's favorable for N2. Well, diatomic nitrogen is more stable because of the enthalpy, not because of the entropy. Actually, having two particles versus one has more entropy. So, okay, and then the last one, dispersion attractions versus ionic bonds. Well, think about which one kind of locks things down in place. That's going to be less entropy. More entropy is when they're more free to go or move around. So now we're to the second law of thermo, and maybe I should back up and say, we already learned the first law of thermo. The first law of thermo was that energy was conserved in a closed system, and that's what we used every time we said that the change in enthalpy for a chemical reaction that all goes to heat is gained by the water. In other words, when the reaction gave off heat, the water gained it all, and we ignored the work because we said no work was done. But anyway, that's what we use, the conservation of energy in a closed system, in the last lesson. Second law of thermo says that entropy always increases for a spontaneous process. And so this is where it gets a little weird. What we mean entropy increases, it may not increase for the substance you're looking at, but it has to increase for the universe. So not just the reaction, but for its surroundings as well, for all spontaneous processes. So the change in entropy for the universe has to be positive. So that might think, well, does entropy have to be positive for a reaction to be spontaneous? No. Okay, because the universe includes the surroundings, and the surroundings entropy can change as well because of being warmed up or cooled during the reaction. So the change in entropy for the surroundings so we need to take that part into account. So here is the entropy, change in entropy for the universe, and this is the change in entropy for the substances. So substances all have entropies, just like substances had enthalpies that we looked up. And so we'll look at the change in the entropy for the substances. And then for this, the change in entropy for the surroundings, that is due to heating or cooling. In other words, whenever the reaction gives off heat, it's changing the entropy of the surroundings, and in a favorable way if it's giving off heat. So that's what we'll be putting together, is how the heating and cooling of the surroundings affects whether or not it's spontaneous. Okay, so we're going to put together these factors, and then the change in entropy when something is heating or cooling is, we can consider this equation for a warming or cooling process. And what else we have? And so we will take the change in entropy for the reaction and put that together with the amount of heat that the surroundings are getting. And remember that the heat that the surroundings are getting are going to be the same number and opposite sign to the heat of the reaction. And so we can plug that in like this. And notice temperature needs to be in Kelvin. This is just putting that together, that the change in entropy for the universe we take into the account of the substances, the entropy of the substances, plus this it looks like it's for the reaction, but this is the heat that is going to warming the surroundings. Okay, so if the change in entropy for the universe needs to be greater than 0, in other words, we need this number to be positive, does being endothermic or exothermic make a reaction more likely to be spontaneous? So if I look at the reaction, if I want this to come out to a positive term overall, I need the heat of the reaction to be negative. That will help make this number bigger. So according to that, exothermic makes the reaction more likely to be spontaneous. If a reaction is endothermic, in other words, if this term is a negative term because delta H is positive, endothermic has that negative sign there. So if this term comes out negative, then I'm going to need this term to be positive and large enough to overcome this one. So if you consider an equilibrium process, and that means a system where you have, whenever you had both the forward and the reverse reactions favorable, so they're occurring at the same rate, that tells you that the difference in the entropy for the two situations must be very similar. And so the entropy would be about 0. It would mean they have similar likelihoods of happening. So if that's true, we can plug in a 0, oops. If that's true, we can plug in a 0 here and rearrange this so that just basically moving this to the other side, so that the change in entropy for the reaction equals this term, that remember this term came from the surroundings, the heating of the surroundings. Okay, and then a slow phase change. So this is like if we're considering we're at equilibrium but we're causing the phase change to happen very slowly, then we can say that this is true, that we're doing this at equilibrium.